And now we are going to transition to something a little bit more concrete, I guess. So I'm a huge fan of Daniel Lemire's posts on the squeezing every little bit of performance out of hardware that we currently have. And today we are fortunate to have him present some of his work on achieving extreme performance of parsing JSON. And so with further ado, let's see what Daniel has prepared for us.
Hello, I'm Daniel Lemire, and I'm going to tell you about data engineering at the speed of your disk. How fast is your disk? You think maybe your disk is slow, but you'd be surprised to learn that many disks today run at speeds that are upward of 5 gigabytes per second when reading data sequentially. Network speeds are even higher. And this means that in a lot of cases, you're not limited by the speed of your disk. I'm interested in data engineering, so I want to consume and produce data at high velocity. In such a setting, if you cannot eat data at gigabytes per second using a single core processor, you may be entirely CPU bound when reading from disk or from the network. What this means in concrete terms is that if you keep exactly the same system, but you replace the CPU by a cheaper one, you're going to decrease your performance. And if you find somehow a way to increase the performance of your CPU by maybe boosting the frequency, you're going to improve your performance. So what if your problem is not the disk or the network? Well, then you might be limited by the memory speed. One thing that people often don't realize is that allocating dynamically memory is a relatively expensive process. So if you look at the following C++, the first line, we allocate a big chunk of memory. This line may execute almost instantaneously, but the memory may not yet have been allocated. As soon as you're going to try to touch the memory, use it, make use of it, it's going to stall because the operating system is going to have to map this virtual memory, that is memory that does not really exist, to physical RAM memory. And this process can be relatively slow. On a Linux server, I timed it at about 3.5 gigabyte per second. So let us assume that memory access is not a problem. So what kind of task can we consider? Let's consider a fairly simple one. So I'm going to take a string of random characters and I'm going to insert spaces in it. So maybe just 1% of all of the string characters are going to be spaces. So this is well motivated. Maybe in your system you have different components that talk to each other, and the code and data is formatted nicely so that it's readable and easy to debug. But at the very end, you minify everything by removing the spaces before you ship it to the outside world. So I'm going to solve this problem using some basic C programming. We look at each character, and if the character value is higher than 32, which is the code point value for the space in ASCII, then I'm going to rewrite or copy this byte. Otherwise, I'm just going to ignore it. This is relatively efficient, and it will nicely remove all spaces. I benchmark this little loop at about 1.6 gigabyte per second on a run-of-the-mill Intel processor. 1.6 gigabytes per second is not bad, but it's far from what even the disk in my MacBook can do. So why isn't it faster? Well, it works byte by byte. It looks at one byte, writes it or not, and then before the next byte can be written, just finish writing it, and so forth. So there's a data dependency between each byte being processed. Now, we know that the processor I was using is running at 3.4 gigahertz. This means that there are only so many cycles per second. And so, because I need one cycle to at least read and write the byte, I'm limited, at least in theory, to a speed of 3.4 gigabyte per second, which is below what best disk can do in bandwidth. Now, why don't I achieve 3.4 gigabyte per second? Well, to do that, I need to be able to read, process, and output the byte within this time frame, so within one cycle, which is of course very difficult because I need to fit a lot of instruction within one cycle. So I need to read, increment, compare, and so forth, and it's really difficult to fit more than say 3 instructions per cycle. So in practice, achieving even 3.4 gigabyte per second on a 3.4 gigahertz processor for byte by byte processing is going to be quite a challenge. So if you can't do it byte by byte, what might you do? Well, obviously the answer is that you have to process it in wider increments. This leads us to SIMD, so single instruction multiple data. It's an old idea that goes back to decades ago, but has been mainstream since at least as far back as the Pentium 4, so quite a long time ago. So the main idea is to build these instructions that can work on several bytes at a time. So the most basic ones that go back to the Pentium 4 work on 128-bit or 16 bytes at a time. So they can do, for example, 16 additions, 16 subtractions, 16 shifts per instruction. So it's quite fast. They're also mainstream in every sense. So you find them in your mobile phone. So your favorite iPhone will have these instructions. They're part of legacy PC. So if you have older machines, they also getting improved all the time. So the latest Intel processors have these this family of instructions called AVX 512, and they're able to work on 512 bits at a time. So basically 64 bytes, which is often referred as a cache line. So it's a big block of data. So with one instruction, you will be able, for example, to take 64 integers, if they fit in one byte, and add them with 64 other integers and get the result. And this will execute easily within one cycle. So it's really, really fast. But even if you don't go that far, just using 128 bits is going to help you a lot if you want to go beyond 3.4 gigabyte per second to reach the speed of the fastest disk. So how might we apply these SIMD instructions to the problem of removing spaces from a string of characters? There are different ways to use SIMD instructions. One of the common one, if you're programming in a C or C++, is to use intrinsics. So these are special functions that are provided by different vendors, such as Intel or ARM, that give you directly access to both the wider registers that are part of these SIMD instruction sets, as well as the corresponding instructions. They're not super pretty. The result is rather difficult to read, as you can see there, and that's a little bit unfortunate. Now, there are different ways to work with SIMD instructions. You can use special APIs that make things a little bit nicer, or you can just hope that your compiler is smart enough to use these SIMD instructions. But in this case, the compiler is probably not smart enough, and I don't want to go into specialized libraries. So let's go with the Intel instructions. So the first line here, what it says is basically we're telling the processor to use a SIMD register that spans 128 bits and fill it with 16 copies of the space character. All right, so it's a flat register that contains just spaces, so 16 spaces. And next, we're going to have the same loop as we did before, but this time we increment by 16 bytes at a time. So the first line inside the loop, we're going to load up 16 bytes of data from our list of characters. Remember, this is 16 bytes in one go. So in this case, we use to load U intrinsic, which basically tells it to load the bytes, and the U stands for on the line. So we don't require the address to be special. So any location in memory will do. The line after that, we use the CMPEC intrinsic to do a comparison between the spaces and basically the maximum between the space values, which are 32, and our byte value, which are x, right? So if any value falls below 32, the max intrinsic will bring it up to 32, and then it will be equal to the spaces, so it will be equal to 32. Basically, anything that falls under the code point value of 32 will be set to true in this any byte register. Then the next line, we basically just, from this 16-byte register, we just basically extract the most significant bit of each byte, which basically will give us a 1 byte value when there is a space, and otherwise it will give us 0. So it's a 16. It will be a 16-bit value with ones corresponding to zeros, to spaces, and zeros corresponding to non-spaces. And then we use a very handy instruction, which is the shuffle instruction, which is a byte shuffle instruction. And what this does is that we take this mask that we computed, we go to a lookup table, and we go recover a register that will instruct the processor to basically just shuffle the bytes so that the spaces out of the way are basically removed. Then we take the result, and then we store 16 bytes of data. And then we have to increment our output pointer by how many bytes, non-space bytes were written. And here we use the pop count instruction to count how many 1 bit we add in the previous mask. So all in all, if you look at this loop, we basically have roughly as many instructions as we did and the more conventional one that works byte by byte, except that now we're really processing 16 bytes at a time. Some of these instructions here are a little bit more expensive, like the pop count is not cheap, so we're not going to quite go 16 times faster, but we're going to be a lot faster. We're going to be, so I measured it at 8 gigabytes per second. So basically, you can remove spaces from a string at speeds that are much higher than any disk can go currently. And I give the hyperlink below the slides to a repository where you can download the different functions similar to this one and benchmark it for yourself and see that I'm not lying. So what else could we look at? Well, another interesting problem is base64 encoding and decoding. So most of our web formats are mostly just text. So whether you're thinking about JSON, HTML, XML, and so forth, it's all text. Our emails are just text, right? So how can we be sending like executable programs or pictures by email? Well, all of this gets encoded into ASCII, so basically text, using a clever format called base64. Now this is widespread. It's you find it at, for example, Amazon has several web-oriented databases such as SimpleDB, DynamoDB, and so forth. And if you want to upload binary data in these databases, you often use base64. If you're using MongoDB, a popular database system, very often, if you have a binary data, you're going to encode it as base64. Elasticsearch, another popular system, will also use base64. In HTML, you have web storage, which is a standard where basically it's a database inside your browser, and again, very often use base64. So once it's encoded, it looks a little bit like this random pile of text. Now the trick is rather simple at a glance. So you take any sequence of 3 bytes. Now there can be any 3 bytes that you like, and then you convert them into 4 specific ASCII characters. Now ASCII characters have the characteristics that are byte values, with the most significant bit being 0, right? And so now base64 does not use all possible ASCII characters. It only uses 64 of them, mostly the uppercase and lowercase letters, plus the digits, and a few other ones. So of course, encoding and decoding base64 data is fast. If you have really optimized C code, you can do it faster than 2 gigabytes per second. You're not, however, if you use just standard C code, you're probably not going to achieve anything close to 5 gigabytes. So you're not going to be able to read off a really, really fast disk at full speed. However, if you use SIMD instructions, you will. In recent work, we showed that if you're using the latest AVX 512 SIMD instruction sets from Intel, you can take 48 arbitrary binary bytes and convert them into 64 ASCII characters using only 3 instructions. Actually, only 2 distinct instructions, but one of them is repeated twice. So you use a permutation instruction, then a special multiply and shift instruction, followed again by the same permutation instruction. And there you have it. You still need, of course, to load and store the data if needed. so it's a bit more than 3 instructions, but it's very fast. If you need to, so this is for encoding into base 64. Now, to decode takes is a little bit more complex because you have to do some error checking to make sure that only allowable ASCII characters are provided as input. So the total ends up being closer to 7 instructions for decoding, but it's still really, really super fast. And so how fast is it? Well, as long as the data fits into the really fast CPU cache of your processor, then a memcopy is faster. But the minute that your memory is not in a very fast cache of your memory, you're basically at the speed of a memory copy, right? So if you're not at the really fastest cache level of the processor, there's basically almost no difference in practice between encoding and decoding base 64 data and just copying data. What else can we look at? Well, okay, so most of the text on the internet is Unicode, and specifically it's in UTF-8 format mostly. Lots of new programming languages or updated programming languages use UTF-8 as a default. For example, Python tends to default toward UTF-8 these days. UTF-8 is basically, well, if the strings would fit as ASCII, then it uses ASCII. So in this sense, UTF-8 is a journal version of ASCII, generalized. But then it can use 2, 3, or 4 bytes to represent a code point or a character, if you'd like. The problem is that there are only 1.1 million valid UTF-8 code points, but we can use up to 4 bytes, which would suggest many more possible code points. So this means that if you just generate random bytes, they're not going to be valid UTF-8 code points. Now, when you're building systems, you need to ensure that your data is valid, right? So if you're receiving from another system some string, before you ingest it and you maybe store it in your database, you want to make sure it's actually valid Unicode. Otherwise, you may very well have garbage on your end. So you need to validate that the input bytes are valid. Now, typically it's done using code that, like you can see on my slide, where basically you check whether you have ASCII. If you have ASCII, you say, I'm fine. Otherwise, if you don't have ASCII, then you get into a stream of branches. Now, keep in mind that on modern processors, a single mispredicted branch may occur cost of upwards of 15 cycles. Just one mispredicted branch, and here you have lots of branches. In any case, this code is not pretty, and it's typically not super fast. If the data is not ASCII, if it's ASCII, this may be quite fast because you only check the byte values, and this may well go very fast. But as soon as you have non-ASCII data, which is the whole point, then the speed falls. So for random UTF-8 data, you have a speed of about 0.3 gigabyte per second. For typical inputs, it will really depend on your system, but certainly you should expect speeds that are below 1 gigabyte per second. And you're not doing anything. This is not buying you much. It's just basically safety. You're just checking that data is sane, that you don't have garbage. And yet, it's relatively slow, like certainly much slower than a typical disk, a typical fast disk. And also, this check may be hidden deep inside of your system where you don't even notice it anymore. So this is quite insidious. So if you've been listening to me so far, you might guess what I'm going to say. Why don't we use SIMD instructions? And indeed, you can. I'm not going to go through the details because it's rather technical, but basically you can do it instead of doing it byte by byte, you can do it in blocks of 32 bytes. It costs you something like 20 instructions, so fewer instructions than bytes. There's no branching, and you can do it without any branch involved, so without any branch misprediction, so no expensive cost, very predictable flow of instructions, and you can achieve speeds that are, much higher than even the fastest disk, so 8 gigabytes or so. On the slide, I give a link to a repository where I run some experiments, I compare different solutions, and you can verify the functions for yourself on your machine and maybe on your workload. So what if you don't care about removing spaces from strings, or you don't care about Unicode? Well, if you're doing any kind of data engineering, you probably know about JSON, and you probably have a lot of it on your hands. So JSON is a fairly simple format specified in 2013, but it's much older. It takes its roots in JSON, as the name might, in JavaScript, as the name might suggest. It's fairly simple. So you have objects, you have keys, you have values, you can store arrays. Fundamental types are integers, strings, booleans, nulls, and so forth, and you have numbers. So parsing JSON is a little bit of a challenge. So what do I mean by parsing JSON? I mean, you have to read all of it, of course. You have to check that it's valid, follows all of the rule. You have to check that, well, again, the Unicode encoding is fine because, of course, there are strings involved. You have to parse the numbers, and you have to build what we call a document object model, which is basically a tree where, for example, inside an array, you can have objects, and these objects can have arrays and so forth. So it's kind of a tree that you can traverse at query time. So if you ask backend or engineers, the type of people who work on big servers with lots of data, they'll often tell you, surprisingly, that JSON parsing or serialization or production consuming of JSON can take up a large amount of the processing time. It can be like half of the time is spent on JSON. And this is a little bit a consequence of how we're engineering modern day web architectures, where it's all little components that have to talk to each other all the time. And doing it via JSON is fine, it's a good design per se. But if the software tools that we use to produce and consume JSON are slow, then the entire architecture is not going to be highly compute efficient. Because I care about performance, I'm going to focus on C++, which is arguably one of the fastest programming languages. That is, it's a language that produces really, really fast code. So probably what is probably one of the most popular software library to parse JSON is a library called JSON for Modern C++. It's really neat. There's a very nice API. It's even though it's C++, you feel like it's really modern. As the name suggests, it does all of the elegance that you would want. When you benchmark it, so here I'm going to use a typical Intel processor, Linux box, and I'm going to use one representative data file that I call Twitter JSON that you can find on my repositories. And to just do nothing with the file, just eat it up and represent it as dumb, as I suggested before, you do it at about 0.1 gigabyte per second. So this is not then the maximum speed of some old school flow disk. So you're really far from matching, the speed of the disk on my MacBook, and you're very, very far from the best disk. Now, this is not to say that JSON for modern C++ is bad code or bad library. quite the opposite. It's a really excellent library for what it is. That is, it's not a library for parsing large amount of JSON really fast. So what if you want to process JSON in C++ really quickly? Well, then you might use Rapid JSON, which is really another really excellent library in C++. That's really, in this time, really designed for speed. And it's much faster. It's at least 3 to 4 times faster than the modern C++ library. And on the same benchmark, I achieved 0.3 gigabyte per second. The exact number will depend on your system, on the compiler, and so forth. But the point is, you're quite a bit below 1 gigabyte per second, which means that you're not within striking distance of processing data at disk speed. So do we have any chance at all of parsing JSON at disk speed? Well, so let's try a little benchmark, right? So I'm going to use the standard library to just access. So I'm going to take my JSON file. I'm just going to access the lines. So there's a nice little function for that that's called getLine. And I'm going to have some variable that stores the length of the lines. And I'm just to increment it with the length of each line. So I'm basically summing the lengths of the lines. Now this is a stupid benchmark. Point is, let's go and see how fast it can go. So I'm achieving 1.4 gigabyte per second. Now this is much faster than Rapid JSON. And it seems, if you look at it, that it should be an upper bound on how fast you can parse JSON. So we can indeed go much faster than Rapid JSON, between 2 to 4 times faster. We have a library for that, freely available on GitHub, called SimDJSON, where on the same file we can achieve 2.4 gigabyte per second. This is without cheating. So we do a full validation of everything. Part of the secret is in the name itself. It's called SimDJSON, so we use lots of SimD instructions. So I'm not going to go into details of SimDJSON because this would take several talks in itself. But I'm just going to illustrate some of the tricks that we're using. So I showed earlier, or you could identify spaces in a string and then remove them. Now, obviously, you can do the same thing with quotes. And of course, when you're parsing JSON, it's useful to know what is inside a string and what is outside a string, just to differentiate things. And so here I give a little routine where if you tell me where the quotes are, I can very quickly, with a few shifts and XOR, I can really quickly compute a mask that tells me where is the inside of the strings. And this is super useful because then I can tell that inside the strings, then I should not look for numbers, or should not look for objects, or should not look for arrays. And what's even nicer is that this little routine with shifts and XOR can translate in reason processors into a single actually instruction, so a carryless multiplication. Now, one thing that you find out if you're doing lots of text parsing or text serialization is that numbers, floating point numbers in particular, are really expensive. So if I give you a stream of randomly generated floating point numbers, say numbers between 0 and 1, and I ask you to use a standard library function to parse them, you're going to be in for a shock. So you're going on a Linux box, you might achieve 90 megabyte per second. So this is slower than most disk I own, really, and it's really surprising. And the cost is just tremendous. So we're talking about 38 cycles per byte. We're talking about 10 branch misses per floating point number. So it's really, really tough. And these decimal numbers appear all the time, right? So they're part of CSV files, they're part of JSON files, and so forth. And if you have lots of them, for example, if you're dealing with geographical data or so forth, this can be a real performance bottleneck. So you can try a few tricks to go faster. So one really nice trick if you're working in C or C++ is this little function there that we designed that can tell you whether the next 8 characters are actually 8 digits. Now this saves you a lot of trouble because you can then use the following function to really turn these 8 digits into one big integer, all in using only 3 multiplications. So this helps tremendously the performance in some instances. So we're currently working on trying to optimize this problem. And basically what we're finding is that most of the strategies that people use to parse floating point numbers go back 20 years ago and have not been revisited in any really significant way. People have been getting a little bit clever about it, and they've using much better heuristics than 20 years ago, and there's lots of really, really clever engineers. But we are in the process of really trying to go much faster. So currently the best we can do is about twice as fast as the Google Epsil library that has a really, 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 really good and really fast function called from cars that it can achieve 300 megabytes per second, which is a lot better than what the GNU standard library can do. But we think that you can, in practice, achieve much greater speed. So right now we're doing twice better. We've posted our code online, and you can run your own benchmarks and see if it stands to scrutiny on your own workload. So even though I've provided many links to different projects and repository that we're working on, the bulk of our work currently is centered around JSON. So I thought I would conclude with a few pointers. So we have, of course, a website. We have a GitHub website. There's lots of contributors, lots of really smart people. It's quite a usable library. It uses modern C++. You can easily integrate it using CMake or a single header. It runs pretty much everywhere, so on any 64-bit system, whether it's ARM or x64, including very old processors. There's no hidden patents. It's Apache 2.0. It's used by a Microsoft project. It's used by Yandex, ClickHouse, a big database by the Russian giant. And it's used by lots of other people as well. There are wrappers in Python, PHP, C#, Rust, Java, Script, Ruby. There are ports in Rust, Go, C#, and we think that it's quite ready to be used in production for people who really want to process data at the speed of their disk.
Yeah, thank you so much, Daniel, for the amazing presentation. It was extremely technical, and I really loved it. I guess then I'll just go ahead and ask a single question because we have time only for one question. is there any other areas that you are exploring for applying similar optimization techniques?
Well, I mean, so there are many things we're working on. Right now, I'm very interested in anything that has to do with Unicode processing, because I think that we're silently spending a lot of time converting strings from one character encoding to another. So that's a very annoying thing. And early tests show that we can go much faster. So basically, my impression is that there's a lot of things that were written a long time ago that they've never been revisited and that we're reusing, but they're very often very far from the best that we can achieve. So, for example, a silly thing that I did a couple of years ago was just look at how we generate random numbers in the interval. So, for example, when you ask for an integer between 0 and 112, for example. Now, that has been done. Like, there's standard libraries. Based on this function, there's a division involved. And division is just about the most expensive instruction that you can do on a processor. And it turns out that it's entirely unnecessary. So you can very easily, with 3 lines of code, do away with that. So that's one of the little things that we did. But it actually exemplified the fact that even when people think that surely we've squeezed all of the performance out of the code that we could hope for, there's very often a lot of slack left. So, I mean, JSON is kind of an illustration of this idea, because when we started out, we assumed that it would be very hard to match the state of the art. And of course, we were able to go much faster by re-engineering really from from scratch. So I think what it comes down to is that it can be sometimes really hard to look at existing code and ask how to make it faster. Sometimes it's really hard, but if you just take it and throw it away and start again with performance in mind, then I think my experience shows that you can often go much faster. So there's basically a limit of what you can do by tweaking existing code and trying to find the odd points and tune them and so forth. Sometimes you have to rethink everything if you want to go really much faster.
Awesome. Looks like we have one question. Can we know more about Go support for SIMD JSON parsing and other SIMD snippets shown?
I'm not involved into Go port, but there are links, of course, online. But basically, what people have been doing is using the ability of Go to basically include assembly output. So what you can do is you have C and C++ code that already work and well tested. You can compile the function, grab the assembly, and then push that into your Go code base, and basically call from Go directly the assembly function. So that's part of one strategy they've been using. And the other component of the question was the other SIMD snippets. Well, I mean, obviously, it gets a little bit it gets a little bit technical quickly when we try to explain these really narrow algorithms. So I intentionally went over them very quickly. But what I can say is that all of the code is on GitHub, of course. And in many cases, we wrote papers and blog posts and everything. So we try to document things as much as possible. But yeah, in one talk, it's really difficult to go into the details. I mean, it gets boring very quickly.
Yeah, awesome. Well, that's actually the advantage, I guess, of a Slack channel. So if there are any snippets or something like that, you'll be able to share them on a Slack. And we have one more question. Do you think we can generalize some of these patterns and push them down the stack, say the compilers?
Well, yeah. So in some cases, absolutely. So the compilers have been getting smarter and smarter, but there are limits to this, because at some point, obviously, it's an NP difficult problem, right? So at some point, to try to ask your compiler to sort of take a whole program and figure everything out is just computationally difficult. But there are also limits to, for example, in some cases, some optimization actually changed the semantics. So it's simply not possible for the compiler to legally take your input and map it to the other. So sometimes to really make use of, say, SIMD instruction, you really have to redesign your algorithm, and you end up with something that has different semantics than the, say, Java or C code. So only for that reason, it can be difficult to imagine that at some point this is all going to be obsolete because the compiler magic. What is absolutely correct on the other hand is that the compilers, and not just C, C++, and Java and so forth, they're really great at using SIMD. But they won't redesign your algorithms around SIMD. That they won't do.
I see. Well, thank you so much. Unfortunately, we have to stick to schedule, so we won't be able to answer more questions live. But there is an extra question in the Slack channel. So if you could stay with us and answer the questions on the Slack, it would be very awesome. So thank you so much again, Daniel.
All right. Thank you.